All right, welcome to Thursday's lecture followed by tutorial for the graph theory. And of course, next week we have a teaching free week. So after today, I'll see you on the Monday of week 7. Let me share my slides, which I will do right now. Okay, hopefully coming through, and I'll just turn my camera off as well. And I did hit record already, so that's good. So what are we actually doing here today? Last time we did most of the connectivity section on Monday. We kind of set out our mission statement for the connectivity section, which was to prove Menger's theorem. But then we first talked about two connected graphs for a while, and we proved that you can build them up from cycles by continually adding things called h-paths, which look like that. So that's fun to play with. We proved a structure theorem for 3 connected graphs, and importantly introduced an operation called contraction that we're going to see in the tutorial today. We stated Menger's theorem, theorem 3.1, which is a min-max theorem, and we deferred the proof until today. And then we saw a corollary, which is about a particular A and B, and we saw the global Menger's theorem, and we proved that one properly, but we kind of sketched the approach of the proof for the corollary. And that brings us to today, when we will give the proof of Menger's theorem, and then we'll have a tutorial on colorings. Okie dokie. And as usual, any questions, let me know in the chat, which I will attempt to monitor. So we'll have to go back a bit over this terminology and notation that we're going to use in the proof. So this picture here, we have two sets, A and B, and they might not be disjoint. An AB path is a path which starts in A, ends in B, and has all of the interior vertices like this, which are outside of A and B. And remember that any vertex in the intersection is itself an AB path of length 0. Okay. Then we had an AB separator, which is just a set of vertices whose deletion disconnects A from B. And this is the definition that we didn't go over on Monday because we didn't need it. You only need it for the proof of Menger's theorem. So let's absorb this definition now. This is meant to be a curly P, and I'm going to try to write it as curly as possible. And this is a curly Q, which I'll probably write like this in the proof. And each one of those is a set of disjoint AB paths. So a set A and B of vertices has already been, two sets have already been fixed, okay? And then both of these are sets of disjoint AB paths, so that's completely disjoint. And we say that Q exceeds P. It's going to be if Q has more paths than P, but it's more than that. It's to do with Q covers exactly the end vertices that P does, and then some others. And same for the end vertices in either A or B. So let's read the definition. Q exceeds P if the set of vertices in A, which belong to the paths in P, is a proper subset of the set of vertices in A, which belong to the paths in Q. So maybe these are the end vertices of paths in curly P. And then I guess I need to include all of those and possibly some more to get curly Q. Whoops, not very curly, make it curlier, okay? It doesn't mean it includes the same paths as P, but it's covering these same vertices here on the left precisely. And then the same thing for B. So actually my picture is not great. Why don't I actually draw that these are some different paths coming out of, that's a horrible picture. Just read the definition, okay? We're covering the same vertices in A using the paths Q that were covered in curly P, but then also some more. It's got to be strictly bigger. It's a proper subset. Any questions about that definition? We'll see it in action very soon. And a last comment on terminology is if you have a path P, which we write x0, x1 up to xk, so all of those vertices are distinct, then we can use, oh, no, now I can't see the pen. Wait a second. Okay, that's better. Then we can use the notation pxi, just meaning the first part of the path p up to xi. Joshua has a question. Let me go back. When I say in no, so it's not going to, it has to, I feel like I'm not being very clear about this, exceeds. It needs to exceed Q. Q needs to exceed P in both A and B, so both sides. So here's a small example. And remember, A and B might intersect. I don't always put that in my pictures. Imagine P was just these two paths. Okay, that's curly P. Then curly Q might be a path that hits those two like this. It hits this one there, and it also hits like this. And so we see that every vertex covered by that was involved in a path in P is also involved in a path in Q, but it's a strict subset. Does that make sense? So because it's a strict subset, it's only going one way. It's like a strict inequality. It's a partial order. Make sense? Okay, cool. We'll see. So this notation, I just want us to absorb. If you chop off the path x naught, if you have this whole path that goes up to xk and you just chop it off here at xi and you keep this bit, then this would be called pxi, okay? And this bit starting from xi and going to the end might be called xip, and that's if this whole path is called p from start to finish, all right? So that's the notation that is introduced here. Now we're going to just state and then prove Menger's theorem from 1927. Cool. Do both include the vertex xi? They sure do. So here in the notation, we see it includes xi when it stops at xi, and it starts at xi for the xip. So that is, maybe if I do this in my picture, then that is more apparent. Okay? Good questions. All right. Menger's theorem, we've seen it before. I'll say it again. How you take a graph, you take two subsets of the vertex set, A and B. The minimum number of vertices separating A from B in G equals the maximum number of disjoint AB paths in G. And this minimum number of vertices separating A from B, it's the smallest number of vertices you would need to delete to make sure there's no paths left from A to B, no AB paths. And in particular, you have to delete all of the vertices in this intersection. And the first thing we'll see is, well, the one half of the kind of, you want these two numbers to be equal, so there's two inequalities. One is easy and the other one takes all the time. Okay, so let's go. We are going to say, let K be a parameter which depends on G, A, and B. It is the minimum number of vertices separating A from B in the sense of the definition that we gave at the start in G. Okay, and now I'm going to say something with the word clearly in it, so we need to look at that very carefully. Clearly, in quotes, K is an upper bound on the maximum number of disjoint AB paths. Okay, and let me put in the scare quotes. Anytime you see the word clearly, you should actually stop and think, because it might mean the person who wrote that didn't really think very carefully about it. I'll just draw the case when A and B are disjoint, but you can also look at this picture up here when they're not. So you can sort of imagine if you had more than K paths disjoint AB paths, all of these vertices are distinct. Going from A to B, in this case 3, if that was bigger than K, so K is maybe 2, and you're only allowed to delete 2 vertices, there's no way you can cut off all the AB paths. And so that would be a contradiction. So we might just write something down about that. So otherwise, deleting a minimum separating set separating A from B would not separate A from B. I guess it really should be an A-B separating set. Would not separate A from B as at least one path would remain. And that's a contradiction. So does that make sense? That if you had more paths than this K, then you're in trouble, because deleting K vertices is never going to kill all the paths, and you can still get messages across from A to B. And you should think about the case when A and B are not disjoint as up here, but it's still true. In this case, I've got 1, 2, 3, 4, 5, 6 elements in my separating set. If I had more than 6 paths, I couldn't kill them all. All right? So can we take that as sort of okay? I'm going to assume your silence is a yes. Let's do the converse. What this means is to get equality, we know that K is the maximum number of disjoint paths, so it's enough to cook up a set of K disjoint paths, K-AB paths, and then we would be done. So let's write that down. This is now our mission. It suffices to prove that a set of exactly K disjoint AB paths exists. Okay. And we're going to prove using induction, a kind of unusual induction. And sometimes to get an induction proof to work, to get the engine of the induction going through all of the steps, you actually have to prove a stronger statement. We're going to prove a slightly stronger statement to get us through this induction. So let's write that down. In fact, we prove a stronger statement involving things exceeding other things. Okay, this is where that exceeds comes in. Let's have a look at our statement. If P, curly P, is any set of strictly less than K disjoint AB paths, all right, then we want to make it sort of replace it by a bigger set, but it's not just going to be bigger in number, it's going to be a set of paths that exceeds Q. So then there is a set curly Q of number of paths in P plus 1 disjoint AB paths which exceeds, in G, AB paths in G which exceeds curly P. So I guess the extra stronger, the reason why this is a stronger statement is that we assume the bigger set of paths exceeds the one you started from, okay, in the sense we saw before. So this is what we're going to aim at through an inductive process. Any questions about this so far? I assume that I'm still broadcasting. Okay. Here's how we do it. We keep G and A fixed, and we're going to let B, the right-hand side, vary in a way that we'll see soon, comma, and we apply induction on the number of vertices in the union of the paths in our collection. The number, of vertices in this union. The union over all paths P in curly P of P. So just the union of all the paths. Okay. And because they're disjoint, that just means you add up the number of vertices in each one in curly P. Sure, that's fine. So we're going to start with the empty set, but the base case will come out in a second. So let curly P be a set of strictly less than K disjoint AB paths. And let B naught be the subset of B be the end vertices. Of paths in curly P. All right, so you've got this set of paths and you just grab all the vertices where they terminate, which are in the set B. Then I'll draw a picture. My pictures from now on are going to sort of assume that A and B are disjoint, and that's not too bad for the pictures, because if they intersect, then you know that each vertex in the intersection is a path, and they're kind of easy and you know what's going on. So I'll just draw it like this. So you've got a few paths maybe, and here is this B naught. What do we know about the fact that B, the number of paths, is strictly less than K? What does that tell us about the set B naught? Any ideas? Yeah, it's got strictly less than K paths, and so therefore B naught, it has strictly less than K vertices in it. And what does that tell us, given the definition of K? How did we choose K in the start? I could show you. Here we go. K is a minimum number of vertices separating A from G in B. But B naught is not that large. So what does that tell us about B naught? That's exactly right. It doesn't separate. So B naught does not separate A from B in G. And what that means is we're going to be able to find another path that we can add in somewhere. And this path is going to be called R. And it's another AB path. Hence, we can find an AB path R, which is disjoint. No, what do I want to say? Oh yeah, disjoint from B naught. That's right. If I deleted just the vertices in B naught, then I would have this new path that still exists, even though maybe I'll draw that again because it kind of looks like a hit. So it's not necessarily disjoint from all the paths in P, as I've shown in this picture, but it definitely gives me a new vertex in B. Separating A from B. Where have I written the wrong thing? Maybe I just said the wrong thing and wrote the right thing, hopefully. Yeah, okay. So we're separating A from B in G. It means after we delete this set B naught, there's still a path from A to the rest of B. Okay, cool. That does sometimes happen, that I say and write different things. Okay. What we now want to do, using our set curly P and this new path, we want to cook up a set curly Q that exceeds P. And there's an easy case that we can write down straight away. If nice condition holds, then we can just take Q to be curly P union this new set R, and it's a set of paths that exceeds curly P, and then we're done. What would that easy case be? Yes, exactly, Joshua. If R was completely disjoint from everything that we've drawn in the black paths, then we could just add it in and there's no harm, no foul. So if R avoids all vertices in that union of P in curly PP, then we can just add R in and we would be done. So now we assume that doesn't happen, and we have to see how to handle it, except that this is actually the moment where we could do the base case. So in particular, if there were no black paths in my picture at all, because curly P was the empty set, then you can always just start off with your first path and you're done. So this is the base case. In particular, this happens when curly P is empty, which is where you start, giving the base case of the induction. Usually in a well-organized induction proof, the base case comes first, but sometimes it's more convenient to mention it later, but you should always make sure that you see a base case. Okay. And so now we suppose that R intersects this union P in curly P of P. And we're going to let X be the last, in a sense that I'll describe in a second, last vertex of R that lies on some path P in curly P. Okay, and last really means closest to B. So we think we're going from A to B. That's our sense of last. So I'll draw another picture that we'll probably see a few times. Similar pictures. So A, B, we've got some paths already existing, and then R comes in, which is new, and maybe it wanders around and intersects a few times, and then it ends up here in B. And X, the last time it intersects in this picture, it's right here, X. Okay? Because I'm saying that's the last time it crosses the black lines. And an important thing is, remember when we chose the path R, we said that this vertex was distinct from the vertices in B0. So what that tells you is X is not in the set B. So I'll just say by choice of R, we know that X doesn't belong to B. And that's an important remark that you should have a think about after the lecture. Okay? Good. Now what we're going to do is, I remember I said in the induction we keep the graph the same. Why is intersection significant? Oh, because to exceed, if I want my curly Q to exceed curly P, it also has to be a set of disjoint AB paths, okay? So this set of paths has to be curly Q is set of disjoint AB paths. And if we just throw in R without worrying about it, we won't have that. Does that make sense, Evan? So I've said that for my stronger statement, because we want a set of disjoint AB paths at the end, we're going to keep that going throughout the proof. Therefore, yeah, okay, cool. So we do have to worry about that. Now, this is the bit where, just to go back to what I was saying, we're going to hold G steady, we're going to hold A steady, but this is exactly the point where I'm going to change the set B. So I'm now going to let, I'll write it and then I'll do something to the picture. Let B primed, this is our new set B, so it's going to be B together with the union of the path XP, so starting from X and finishing along P. Oh, I haven't defined, oh no, I did define P. So P is the path where X lives. So in my picture, a bit hard to write, P is this path here, okay? And I'm going to take that part of the path from X to the end and from X to the end along R. And I'm going to add all of those vertices here into the set B. It becomes B prime. So this is the vertex set of those two end portions of the path after X. Okay, so I don't know if my picture is now helpful or not, but that's what we do to B. We make it bigger. So it's strictly bigger because X doesn't belong to B. And I'm going to adjust my set of paths curly P so that I get a new set of paths curly P primed that goes from A to B primed. So the only one I have to adjust is I need to take P out of it because P has X and then some more one more vertex in B. So, well, a few more. So we have to get rid of P, but what I add instead is the initial segment PX. Okay? Because this initial segment, at the risk of making my diagram way too involved, that's this bit here. Okay, PX is fine because now X is an element of B primed. And so this here is the old P. I'll draw a new picture soon. But that's what we're going to do. Okay, we've made B primed bigger. The number of vertices involved in P primed in the union of all the paths has gone down and we can apply our induction. So that's what we're going to remark. We still have the same number of paths, but the union of paths in P primed has fewer or strictly less vertices than, I'll write it all out again, the union of paths in P, curly P, and that's basically because you've lost X, if nothing else. And because of this, we can apply, oh, one more thing, but we will be able to apply induction in a second. One more thing is we need to think about K, what's happened to K. So if I want to separate A from a set B primed, which is now bigger than it was before, what could that do to K? So I want you to tell me less than or equals or greater than or equals here, and it's because B is a subset of B primed. So do you think it gets easier or harder in terms of the number of vertices you have to delete if you want to separate A from B primed, which is bigger than what you were separating A from before? Yeah, it's going to be harder because B prime is bigger. It might include some vertices of A that weren't in there before, and so the value of K cannot go down. It can only get worse. So K of GAB primed is greater than or equal to K of GAB, and what that says, the reason why we mention it is an A B primed separating set or maybe this shouldn't be so, but it's just like a remark, is also, or maybe it's part of this since, it's also an AB separating set. And you need this to think about getting the inductive step working. The point is the size of P primed, the number of paths in P primed, is still less than K for the new setup. So the inductive hypothesis applies. Hence, we can apply the inductive hypothesis. So you should think about these details later and just check that it all works. We apply it to GAB primed. We conclude by induction that we can embiggen P primed to Q primed. There is a set of paths curly Q primed which exceeds curly P primed. That's what the inductive hypothesis says. So we conclude that there is a set curly Q primed. We've made curly P primed bigger by 1, but we also know that curly P primed has exactly the same number of paths as curly P. So it is in fact a set of curly P, number of paths plus 1 disjoint, A, B primed paths in G, okay, which exceeds curly P primed. Phew, right, excellent. Now we want to take this set curly Q primed and kind of adapt it, going back to this picture of how we made B bigger. We want to adapt it to come up with a set curly Q of AB paths, which exceeds our original set of paths. So that's what we now want to do. Okay, there's a lot going on here. So let's make a couple of remarks. Because curly Q primed exceeds curly P primed, okay, we have this. It contains a path Q which ends in X. Okay, we know that because curly P primed had a path ending in X, and that's what exceeds gives you. We definitely have a path Q in curly Q primed ending in X. And furthermore, it has a unique path, which I'm going to call Q primed, and that's why I'm trying to be clear with what's curly and what isn't, because it makes a difference. A unique path Q primed whose last vertex, the one in B primed, is not one of the last vertices of the paths in curly P primed. Okay, this is the path that's giving you something new in the set B primed. We're calling that Q primed. Okay, and in particular, I think the last vertex of Q primed needs a name. It is called Y. The last vertex, Y. Okay. In particular, Y is not equal to X because X was one of the last vertices in a path in P primed. In particular, Y doesn't equal X. All right. And now we're in good shape. What we're going to do is think about this question. Where could Y be? Okay. So I might draw this again. And I'm going to simplify this picture so there's less for us to look at. So the sum, oh yeah, we had a path P before and our vertex X was on it. And we also had the end of a path R, which I used to have in red. So let's do it in red so that it all makes sense. So this red thing is X. Oh no, my battery's running low. How is that possible? Everything should be turned on. Hang on a sec. Wow. That's very bad news. Let me just check, make this smaller so I can see my battery. Why is it not charging? Oh, I'm panicking now. Okay. I'm just checking every connection that I have. Oh no. Sorry about this. Is it now charging? No. What do I do? Sorry, I just want to make sure this is charging because otherwise, oh, it's going up now. Is it? I don't know. Let me just keep going through this proof. Sorry, I don't know what to do because it's not charging. Hang on. I'll just keep going. If I stop, then I'll readjust. Sorry about this. Okay. Don't tell me. I mean, the house can't have lost power. Anyway, where could Y be? We have this path Q, which is where we want to know where Y could live. Oh, sorry. I beg your pardon. Q is the one. Start again. There's X. I'm only going to give you, this is XP. Okay, this is XR. We have a new path, Q, that ends in X. And somewhere we have a Q primed that ends in a new vertex Y that we haven't seen before. And basically Y could be in B, or Y could belong to XP, but not B. Okay, or Y could belong to XR. And those are our three cases, because remember we chucked all of this stuff into B to make B primed. So hopefully that makes sense, the three options for Y, and we're going to look at these three cases now. Cool. So if Y belongs to B, then I'll draw this picture again. We have Q going to X, we have an XP, we have an XR, and we have some that ends in Y. Oh, I think I've died. I'm really sorry about that. Let us now continue. We want to prove this damn theorem. Where could Y be? All right, I think we need to review. We applied induction. We have a set of paths curly Q, which is the right size, but it is from A to B primed. And now we need to adjust curly Q to give us a curly Q prime to give us a curly Q, which goes from A to B. We know the Q prime contains a path Q ending in X and a path Q primed ending in a new vertex Y. Where can Y be? All right. Yay, I know. All right, so if Y belongs to B, which is as in this picture, this is the, well, maybe you can tell me. We let curly Q, oh sorry, just curly Q, be obtained from curly Q primed. We have to take out simply the path that ends in X, because we don't want paths that end in X anymore. And every other path is going to be fine. So we get rid of Q and we have to replace it by something. So does anyone have a suggestion for what we could replace Q by? Or a description of a path that will do a good job? It's a bit hard to ask you a question after all of that. But we've got this set curly Q primed of paths. and we just need to replace the one highlighted in yellow there that ends in X with something that goes all the way through to B. Any suggestions of which bits of paths we could use to do that? I think perhaps I'll just tell you. So what we can do is we can use, for example, QXP. So we go along Q until we get to X, and then we travel along P, okay? And that will get us to here. And I think the only way you wouldn't do that, yes, thank you, Evan, that's right. So that would be unless Y belongs to XP, in which case, I can't even do words anymore, case, let you use R instead. So either way, you'll be able to avoid curly Y. If the first option doesn't work, the second option definitely will work, okay? And either of those ones, you choose one that works and it's all good. Next, we're going to look at, actually in my notes, I've got Y belongs to XR next, so let's just do that one. QXP is the P that we started with from before, that's right. So X belonged to a path P in the original set of paths, and that's what we're grabbing. Okay, Evan, Q originally, it's the path in curly Q primed that ends in X. So it's from the new curly Q primed and it stops in the wrong place, so we need to sort of extend it. Okay, so unfortunately you're going to have to, oh my God, we recorded that whole thing. I never stopped recording. Oh no, I should have stopped the recording. Oh dear. Okay, so what we want to do next is consider if Y belongs to XR, but it's not at the very end. So Y is not in B, then we're going to see what happens. So let me draw another picture. So here's A and B. Here is Q that ends in X, and we have XP from before. We have XR also from before, and we have, oh no, I've done it the wrong way around. I want to put that on the top so I've got more room. Let's stick XR up here. And we have this Q primed that ends in Y, Q primed. So we can see that we have to change both Q and Q primed. We're going to delete those. So we're going to take curly Q to be curly Q primed. We have to change both Q and Q primed. And can anyone see two very nice paths that will get us from A to B and don't intersect? XQXP, yep, and Q primed YR, that's exactly right. So you want to take this part and this part, and you can see that they don't intersect. So we take Q all the way to X, which is the end, and then we travel along P until we get to B, and Q primed to Y, and then we go along R because we've assumed that Y is on XR, okay? And that is just an old picture, and luckily we're almost finished. So the final case is that Y belongs to XP. Finally, if Y belongs to XP and Y is not in B, because if it was in B, then we could have dealt with it before in our first case, then we have A, B, let me just have a look at the picture. Oh, I didn't do a picture. So XP, XR, and I guess we're going like that. So we've got Q going up to X. This is Y. This is XR. And this in there is XP, is this part. And we're going to do something similar. So Q primed, curly Q primed, curly Q, sorry, is curly Q primed. We have to take away Q and Q primed. Both of those paths are no good, but we want to add what? So again, you just have to look at this picture and identify two disjoint paths from A to B. Yeah. So it's this time you go along Q to X, and then you go down along R, and Q primed, which was the green, I didn't label it, from Y, and then P. So this was Q primed, and that's what you do. So it is Q, X, R, comma, Q primed, Y, P. Okay, Q, X, R, yep, that's correct. And then I'm just going to say a few words to end this off, and I'll do that over here. In all cases, comma, curly Q is a set of the number of paths in curly P plus 1 disjoint AB paths which exceeds curly P as required, and that is the end of the proof. Because it means the induction will keep going until you've got enough paths, which does a set of K paths. We showed that we can keep going until we have K paths. Okay, any questions about that? That's never happened before in the middle of a proof of Menger's theorem. So D still gives 3 different proofs, and I've decided that this proof is actually the most understandable of the 3 proofs, but if you wanted to look at some other proofs of Menger's theorem, you could do that. So this completes the lecture content for chapter 5. Any questions on that? Okay, because we've had a bit of a disruption with the lecture with my issues, why don't we start the tutorial at just in 3 minutes, okay? Tutorial at 1:15, just so we don't lose too much time, and my apologies for that. I'll stop the recording and start again when we're going with the tut, okay? Thanks.